Hello and welcome to episode 7 of our language design exercise using the Ohm Language Library. In the first 6 episodes, our language has developed quite a bit, and we've worked quite a bit on the syntax, but there are some things we should really look into. We should start looking into how is this language going to be processed at the semantic level? What kind of, how have we done specifically with types? And it's a good time to take a review of our type system right now and see if it kind of works. So we've attempted to make this language statically typed, meaning we have type constraints in all the variables, and every time you look at a expression, you know what its type is. And we've gone kind of overboard on that in a way, right? You might remember that every variable declaration requires both a type and an initializer, meaning we write things like let s be a string. And this is good code right here. A little redundant, but hey, we're being really specific. Manifest typing, they call it. We've been careful to do things like the following. We can allow ourselves to make arrays. We have an array type. This is an array of strings. We can even have an array of optional strings if we wanted to. There's a lot that can be done here. We made sure actually that if we had an empty array, that empty array by itself was not appropriate. We would have to say of string, because we were trying to remove type inference. Like, we always wanted to be able to look at an expression and absolutely know what its type is. So say we wanted to print something like this, right? Can't print this, that's illegal, that's red, but okay, we can print this, that's fine. We did similar things for dictionaries too, right? If you want an empty dictionary, no, we have to say exactly what kind of dictionary it is in order to make it right. So we've tried to be really manifest, but if you think about it, how did we do? I mean, do we never have to do type inference? Well, we don't have any type qualifiers on our array literals that are non-empty. There's nothing here, right? And in fact, since there's no qualifiers, what's really stopping us from doing this? By the way, now what type is this? An array of what? Does it even have a type? In our language right now, this actually does not have a type. So we might think about what something like this means. And maybe one thing we can do in our language is simply just reject it. Or we can try to embrace it. Now, either way, whether we embrace it or reject it, we have a case where we still have to do type inference. I mean, unless we said something like, of int array or something like that, which is not part of our syntax. I mean, right now, we still have to do type inference, right? We just cannot look at this and know its type without doing some computation in our compiler, interpreter, and language processor. So are we going to embrace type inference? Are we going to do the Java thing? If you've seen Java before, you write things like this. You say new integer array, and then put your contents in here. It's a way to say, look, okay, I'm specifying the type, so you know what the type is. Then you can type check it. Type check just this expression right here without looking at anything else around it. So no, there's no inference. There's nothing contextual that needs to be done. So for us, we're trying to think, what should we do here? Do we want to embrace or just reject it? And I would argue here for embracing it. I mean, I want to see what else we can do with type inference. So let's say that, okay, this type inference is here, it's going to stay. And since we have to do type inference like this, since there's nothing required to put on here, we have to be able to deal with things where there's mixed types inside of an array. Embrace it or reject it? Well, let's see what it means to embrace it. This is no longer an array of ints or an array of strings. It's an array of something else. It's basically, what should we say, an array of anything. Okay, it's syntactically correct, and that's fine. We want it to be syntactically correct, but let's think ahead to semantic analysis and see how we're going to deal with it. And I would say, all right, let's deal with it by creating a new type. Let's create a new type called anything. Our type will be anything. It's a nice long name, but what are you going to do? And we're going to make that a keyword like the other types. Anything. Remember doing this? Crazy, huh? Anything. And still passes, right? I mean, we didn't do anything different, but what we want to check for anything to try to test to make it work is, let's deal with trying to say something like, let A be an array of anything. Let's see if we can actually specify the type here. And yep, it's green, so we're allowed to do this. So anything is actually a type. I guess we can also say, I mean, A can be anything and be a string. I mean, that's fine too, but anything will be a type. Once we make anything a type, okay, that's kind of cool, because now if you think about it, now that anything is part of our type system, I think we can actually just deal with these lone empty arrays, right? Because we're embracing type inference. We no longer have to specify types on our empty arrays. I mean, we forgot to specify them on our non-empty arrays. So why don't we just get rid of them over here? Because this was kind of ugly code anyway. So let's get rid of our empty dictionaries. Let's get rid of our empty arrays. And let's make our array literals and dictionary literals permit emptiness without type qualification. And they do. Now we're fine. We can actually print this. We can print an empty dictionary and things are okay. We don't know what the type, or we do know what the type is actually. This is array of anything, which is interesting because now if I were to say something like, let A be a string array, we now have an array of anything, and now this is a type constraint that says array of strings. We'll have to let our semantic analyzer figure out type compatibility rules. But syntactically, we'll like it, and we could see a case where this is a fine conversion. Speaking of conversions, there may be times when we want to actually do a conversion. For example, what if we found ourselves doing something like this? Okay, I think we want this to be a type error, right? Can't assign an integer to a string. But what if we wanted to convert an integer to a string? Yeah, we could put something like, you know, like in a type library, we can include a parse int or toString or something like that. But there's another way that's kind of nice, and that is to use a new keyword over here that says that we are doing a type conversion kind of explicitly, you know, where we specify the type we're converting it to. Now, in a language like Python, that's not what I wanted to say. I want to say string, of course. Python, you would write things like this. All of the types actually look like they're function calls. They're actually callable. But in our language, I think I'm going to go for this new keyword as to do a type conversion. And I'm going to add the word as right here. As is going to be the word as, not followed by an alphanumeric, so it does not get confused with an integer. We'll drop as in here. And as a new form of expression, let's allow a expression to be cast with as to a type. We'll call this a type conversion. And we have something working here. I decided to go with parentheses right here because it's hard to figure out precedence, I think of it, of as, right? I mean, if I say 5 plus 2 is string, is it 2 as string, or is it 5 plus 2? Does as have high precedence? Does as have low precedence? If you shove it in the middle, I don't know, it might be confusing. So just require the parentheses to be done with it. And by the way, now that we're doing all this type conversion and type inference, all this good stuff, you ever thought about whether or not, this doesn't work right now, but have you ever thought whether or not it was useful to be super manifest in your typing? Like, when you have to put in this type constraint right here on your variable, even though you're looking at an initializer right here, I mean, some people are like offended. It's like, don't make me say it's a string. I know it's a string. And some people like the crutch where they say, oh yeah, I'm gonna say it and I can read it. Now I actually know everything that it says. I'm fine going either way. I'm fine with things like this. But if you want to specify the type, you can specify the type. And you probably should have the ability to specify a type now that we got rid of type constraints on empty arrays, because something like this, okay, it's workable, but yeah, okay, so here message is an array of anything, but maybe what we wanted to do was say, no, I want this to be an array of strings, or I want this to be an array of Booleans, or I want it to be something like that, right? So we should be able to put a type constraint on a variable that we declared anyway, even though an initializer is there, and we can infer the type of initializer and copy it over, right? If we don't specify it, it's going to be an array of anything, but if that's not what we want, we should be able to put a type constraint on if we need to. Oh, and that leads us to the question of what about parameters? Well, I would totally be in favor of having the type constraints on parameters to be absolutely required. You really can't infer them anyway, right? We only do type inference if we know it's being assigned to it. And remember that f can be called from different places. F can be called somewhere here, and maybe it can be called from here as well. And you can't just really infer that this is supposed to be an int. Like I can't leave this off and say try to infer it because you got this and this. And okay. So sure, you can say, oh yeah, no, we don't need to infer it. We'll just say, or I'm sorry, you can say, yeah, let's just infer it that it can be anything, right? So why not just have it be anything? I mean, you can put it there, but I think for this language, I'm going to leave in the fact that type constraints must appear on parameters and they must appear in function returns. But for local variable declarations or global variable declarations, just plain old variables, we don't need them. Let's do type inference there. So we've actually, in some sense, complicated the grammar with 2 new keywords and a new type conversion operator, but we've actually cleaned up things a little bit when it comes to arrays and dictionaries. And now we're allowing the more natural empty array, which needs a semicolon, and the more natural empty dictionary. We could go one step further and start dealing with nil, where the type conversion here would be anything question marks. Do you want to add the keyword nil? I don't know if I would probably go that far. I think I'm fine with this old no type. I don't know. It's just preferences. There's no accounting for taste. If you don't like it in your own language, build whatever you need. Okay. By the way, this actually passed because nil is an identifier, and remember only checking syntax. So nil is just an undefined identifier, and that's fine. Again, if you want to build your own language and do some different things, feel free. But in this episode, we've taken a look at types. We've embraced type inference. We created an anything type, and we've created type conversion with as, and we've cleaned up our empty array and dictionary literals. In the next episode, we're going to do the fun stuff. We're going to be doing concurrency. So see you then.